thanks for being here for unusual time and unusual place. And I'm very, very happy to introduce Emanuel Todorov from UC San Diego. He came from Bulgaria. He was a superstar in math and computer science. When in Bulgaria, he heard the best university to go to is called the West Virginia University. So that's where he started. And at that university, he heard the best place to go after that is MIT. I don't know what he was thinking, but so he went to MIT, and that's where I actually met him. And since then, he's been just a leader in the field. He went to Gatsby Computational Neuroscience Unit in London, then to USC for both postdoc, and now he is a faculty member in the Department of Cognitive Science at UCSD. He is really a true leader in the field of computational neuroscience, where what he says, every word seems to be worth quite a lot, and everybody seems to follow whatever he says and try to do research similar to his. So without further ado, this is Emanuel Todorov.
Thank you, Yoki. Now I better be careful what I say. So I'm interested in how the brain controls the body and makes it move. And since most of us live in offices, I'm going to remind you that there are animals out there and they do pretty amazing things. So nature is full of examples of amazing control systems that do very impressive things, and they're still better than any control systems that we have managed to build for the most part, especially in robotics. So I want to understand how the brain controls movements and makes animals accomplish goals on the system level. I'm also interested in how the neurons that are controlling this behavior are operating. And at the same time, I'm interested in how do you solve hard control problems. You know, as an engineer, how do you build a control circuit that gets a complicated body to do complicated things? Now, the methodology I use is optimal control. The idea is that you want to control things in the best way possible. And in the case of animals, that makes a lot of sense because animals have evolved, and evolution is basically an iterative optimization process. It makes behavior better and better, and the animals that don't perform very well don't make it, and the ones that perform better, they tend to make it. So optimal control is a natural framework for studying biological movement. It's also good for engineering because obviously every engineer would like to control their machine in the best way possible. And so in engineering, the answer is not should you do optimal control, the answer is can you do it? You know, do you actually have the algorithms to figure out what is the best way to control a machine? So my work has to do with both developing that's the last word of evolution. So my work has to do with developing algorithms for solving optimal control problems and using them to build models of behavioral data, and also more recently using them to build models of neural data. And I'm going to talk about each of those a little bit. So on the algorithmic part, but actually, sorry, before I start, let me just say one more thing about optimal control. So it's motivated by the fact that optimal is optimal, which is good. Also, evolution seems to have a lot to do with it, but also as a methodology for building models or theories in science, it's really good. And it's good because it allows you to start with very parsimonious assumptions that are sort of sensible and simple, and get very elaborate predictions. And that's key to any theory in science. You want to assume little and explain a lot. That's sort of Occam's razor. So let me just use that as an example to introduce some methodology, terminology in optimal control. So here we have a dynamical system. It's a simple sort of point mass that's moving on this hill, and it wants to park. It wants to go to that position and stop. Control signal is just a sort of tangential force, and the state is the position and velocity of the car. Okay, so the cost function has two terms. The first term is some state-dependent cost that specifies what we want to accomplish. So in this case, we want to get to a parking lot, so we want the position to be equal to whatever this is, and we want the velocity to be 0. So if you get to this blue region, the cost is 0, you're happy. You're outside that good region, the cost is some constant bigger than 0, and you're unhappy. So you keep accumulating large cost until you park, and then it's good. Okay, and then along the way, you sum up all the control signals squared. So this is like an energy term that encourages fuel efficiency, which seems to be becoming more and more important. And that's for people like Yoki who still drive SUVs. And then there is some state-dependent cost that really captures the notion of a task. What do you want to accomplish? So these are the assumptions that you put in an optimal control model. The dynamical system is not really an assumption, that you know what that is. So the cost is the assumption. What you get in terms of prediction are something much more elaborate. So this is the main quantity that you work with in optimal control. It's called the optimal cost to go function. It sometimes also called the optimal value function. So it's basically one is big, the other one is supposed to be small. What this function means is the following. If you put the system in any state, say here, and you act optimally from now on, how much cost are you going to accumulate? Okay, so it's the best long-term performance you could ever achieve with that system. And it's some function, some well-defined function. There are ways to look for it. In this case, this is computed using dynamic programming. But the point is that this is a lot more elaborate than this. So when your assumptions are in this form and your predictions are that elaborate, that's good. That's at least we're on the right track. Now, whether your predictions agree with data, that's another story. But at least to have a good way to sort of turn an automated crank and turn something very parsimonious into something very elaborate. Once you have this function, it's easy to compute what the optimal control signals are. So in this case, the control signal is a scalar, so it's just a scalar function of the state space, and it's denoted with this color plot here, and this is some trajectory. So for example, in this case, it discovers that if you start at 0, 0, so if you start at this position with 0 velocity, the optimal thing to do is swing back and then go over here. This is what this spiral does. Anyway, so this was just a simple example. Now, most of the problems we want to solve are much more high-dimensional and complicated, so we need powerful algorithms to do that. Indeed, optimal control is one of the hardest problems that you can try to solve numerically, and it suffers from the curse of dimensionality and other sort of issues. So over the past few years, we've actually developed several classes of models, and obviously I don't have time to talk about all of them in detail. I'll just talk about one of them in some detail and briefly mention what the others are. So the first thing we did takes the standard sort of linear quadratic Gaussian framework. What that means is you have linear dynamics, cost functions that are quadratic in the state and the control, and additive and Gaussian noise. So this is the one class of optimal control problems that you can solve easily in sort of closed form. And what we've done is we extended that to add noise that depends both on the state and the control variables, and that makes them very suitable for modeling various behavioral experiments, and we've used them in a number of papers. The code is available on my website, and other groups are now beginning to use those. We're also using recurrent neural networks to approximate an optimal controller and then see what happens inside the network, and I'll talk about that. We're using a hierarchical approximations to optimal control, and I'm going to talk about those as well. This is something I won't have time to talk about, but I'm just going to show you a demo, which is actually not my demo. So there was a technical report sitting on my website, and a couple of really good students in Israel found it and implemented it and used it to do something really cool. So this is actually based on a NIPS paper that was published last year. So here's a little swimmer. So this is a 14-dimensional nonlinear dynamical system. And you can give it a target, and it sort of swims to it optimally. And you can see that it gives rise to all these emergent behaviors. So it has this cyclic thing, and then it has a cruising phase, and then sort of stops somehow. And it can go to arbitrary targets. So this class of algorithms are very powerful. Actually, I believe most of you saw Peter Abeel's talk a couple of weeks ago where he was flying helicopters. That is, those helicopters are flying using an algorithm that's in the same family. It's called differential dynamic programming. So that's the first algorithm in that class. We've been building sort of more extended and more robust versions. And the idea is basically to start with some control law, see what trajectory it gives rise to, and then analyze the problem locally around that trajectory and find a way to improve the trajectory, and then analyze it again, and then it tends to converge very quickly. So unfortunately, I had to leave this out of my talk, but you can read on my website if you want. Another thing we've been very interested in is the trade-off between exploring and controlling things. So for example, if you're manipulating an unknown object, you have to manipulate it. You have to make sure it doesn't fall and does whatever you want, but at the same time, you have to learn about its properties. So the same movements are accomplishing two goals. One is basically a system identification goal, like putting noise into a system, seeing what it does, and the other one is a control goal. And those two tend to be at odds with each other, so how do you resolve that conflict? And we found a way to formalize that mathematically, and we just had a paper in the American Control Conference that you can read about. So the thing that, I just had to gloss over all of that because there are many other things I want to tell you. The thing that I'm going to tell you in some detail is this last thing. So this is sort of the most exciting thing that I've been working on recently. I was here a few months ago, and I described this in some detail. And I'm giving a talk in applied math on Wednesday, where I'm going to cover this in full mathematical glory. So for the present purposes, I'm just going to summarize sort of the main results and show you some applications. So what this is I've developed a class of stochastic optimal control problems which can be reduced to a linear problem. So basically, it comes down to solving a linear system of equations. So for discrete systems, you end up looking for the largest eigenvector of a matrix. For a continuous case, you end up solving a linear second-order partial differential equation. And that's a big simplification because optimal control usually comes down to nonlinear Bellman equations. So let me tell you what these control problems are. So first, let's focus on the discrete dynamics case, and then we'll see how generalized to continuous cases. Okay, so in this simple example, suppose you're some agent moving in some discrete world, say a graph. It's a graph navigation problem, or some sort of grid or maze. And suppose there are 3 possible next states, 1, 2, and 3. And suppose you can take the action, which is labeled with the symbol 1, and what that really means is that you have a high probability of transitioning to state 1, and lower probability of transitioning to states 2 and 3, and similarly here. Okay? So when we talk about actions in Markov decision processes, which is another name for discrete optimal control problems, what we mean is that there's some sort of symbols that actually correspond to some transition probabilities. Okay? Well, now we can plot the simplex of all possible transition probabilities. It's this triangle, there's a positive number that sum to 1. And then the symbolic actions that are used traditionally are just discrete points in that simplex. Okay? And that makes optimal control hard because optimizing over a discrete set tends to be hard. And at the end of the day, it usually comes down to exhaustive search, which is no good. So what I did is I said, well, let's allow any transition probability distribution here to be accessible. So in other words, the controller can decide what the dynamics of the system should be, how it wants the system to behave. Okay, so it can pick any point here. Now we're also going to pick some special point here, denoted p bar, which you can hardly see. And that corresponds to a notion of a passive dynamics. So passive dynamics means what does the system want to do on its own if you don't control it. Okay? In continuous systems, that makes a lot of sense. You know, any robotic system works, for example, my arm, if I let it fall, it does something. In discrete problems, this is not usually used, but I'm introducing it here because it's very useful. On a graph, that would normally be a random walk. Okay, so have some passive dynamics. You can pick any transition probability you want, but you're going to pay a price. And the price is the difference between what you picked and this passive dynamics. Okay, and so both of these are probability distributions. The natural way to measure differences is something called KL divergence, or Kullback-Leibler divergence. I should be careful with this thing. Right, so now the cost functions we're going to allow are of this form. You can define any state-dependent cost that you want, and then you're going to pay an energy cost, basically, which is the difference between the controlled and the passive dynamics. Okay? In the continuous case, this here's the following picture. So you're some state, in some small time period, the passive dynamics is going to take you somewhere, and this is some probability distribution here. And then the active dynamics may take you, or the control dynamics may take you somewhere else, and then the control cost is just the KL divergence between those two. And it will turn out that for the class of problems we're studying, this KL divergence is just the quadratic energy cost that people normally use in control. So this is just a pictorial sort of overview. I can just write down formally what these problems are. So in the discrete case, the dynamics are the following. You choose the transition probabilities. Okay, so xt is the current state, some transition probability function, next state is sampled from that. There's a cost that has a state cost, and this KL divergence between what you picked and some passive dynamics. On the continuous side, we have a nonlinear diffusion process. Basically, there's some nonlinear drift and some gain matrix, and that's the control signal, and the cost has to be in this form. Okay? So I've been able to show that. Go ahead.
So this passive thing for the discrete case, would that be something like a stationary distribution, or what would?
No, the passive dynamics is some sort of transition probability distribution. If you iterate that forever, that's going to lead to some stationary distribution. Okay, so I've been able to show that for both of these problems, you can define a function which is the exponent of this optimal cost to go function. We're going to call it z for the rest of the talk. And then the equations that you have to solve are linear in that Z. Okay, so the so-called Bellman equations, or Hamilton-Jacobi-Bellman equations, transform into linear equations. So in the discrete case, it's this Z is just the exponential state cost times the expectation of Z at the next state. And the next state is sampled according to the passive dynamics. Okay, so two things to notice here. One, this is a linear equation. There's no minimization or anything else. All of that has been taken care of analytically. And two, you can actually solve that by sampling, right? Because this gives rise to sampling methods, and I'll show you that later. In the continuous case, it leads to second-order linear partial differential equation. It's not at all obvious why this is so. You can read the papers on my website to find out, or come to my talk on Wednesday. So the other fascinating thing about this family of control problems is that they end up being dual to Bayesian inference problems. Okay, so dual in the following sense. So on the bottom here, below these arrows, I've written the corresponding Bayesian inference problems. In the discrete case, it's basically a hidden Markov model. So here you have some state that's evolving under the passive dynamics, P bar. You don't observe the state directly. Instead, you observe some measurement. Measurement is just a 0 or 1, and it's sampled from a Bernoulli distribution with rate R, which is some function of x. Okay? And to make the two problems dual, you have to set this cost related to be the log of this R. Again, for reasons that you can find in those papers. Here, the estimation problem is the following. The state evolves according to the same dynamics as here, but without the control signal. And there is some sort of nonlinear measurement. And to relate the two, you have to make the state cost equal to this. Okay, so in both of these cases, we can show that the posterior probability distribution in the inference problem is proportional to the exponent of the optimal cost to go function. Okay? So what that means is that this is the class of optimal control problems that have exact duals in the estimation domain. Now, you probably know that such duality was first described by Kalman. So the Kalman filter is dual to the simplest optimal control, which is called the linear quadratic regulator. And that applies to linear systems with quadratic costs and Gaussian noise. This is a nonlinear generalization of that result. Now, this gives rise to a number of efficient algorithms for solving optimal control problems numerically. I'm just going to illustrate a couple of them. So the first one is a new method for discretizing continuous problems. And this is possible because it turns out that these problems here can be obtained as limits of these problems when certain time step goes to 0. And again, the limiting process is somewhat technical detail that involves stochastic calculus, and it's not shown here. But because these continuous problems are limits of those discrete problems, what that means is that we can step away from the limit, use some sort of finite time step, and then these discrete problems can become discrete versions of these continuous problems. Okay. Now, it's very common to take a continuous problem and discretize it and turn it into a Markov decision process. And when you do that, you discretize both the state space and the control space. And then you apply dynamic programming. Okay. Here, we only discretize the state space. And the optimization over the control space happens analytically in closed form. And because of that, we get faster approximations. So this is shown here. This is my little car on a hill problem. This new algorithm I'm calling Z iteration. You can see how fast it converges. This is policy iteration with various parameters. There's another dynamic programming algorithm called value iteration, which is something like that. It's really slow, so it's not even plotted here. And you can see that the two basically give you the same solution. That Z iteration is something very simple. It looks like this. So you're looking for a vector Z, one number for every state. P bar is that's passive dynamics. It's a square matrix containing all the passive transition probabilities. And this is the diagonal of the exponentiated state cost. It's a very simple algorithm and converges much faster than dynamic programming. Yes? Why aren't they the same? Because these are two different approximations to the same thing. In the limit, when you make the time step 0, they're going to become the same. Away from the limit, there are two different approximations. This axis actually shows what is the cost that you get when you apply it to the underlying continuous problem. So you can see that they converge to the same level. So they're equally good approximations, but they're just different. It's a good observation, though. Wow. People really notice the small differences here. I guess you have to work in computer vision to see such things. I mentioned earlier that the equations that this Z satisfied look a lot like sampling, and indeed you can come up with a learning algorithm which is based on sampling. And it's an off-policy algorithm. So what off-policy means is that you control the system according to one control policy, and at the same time, you learn about the optimal policy. Okay. Reinforcement learning is I assume you know what it is. Basically, it's a branch of machine learning that tries to solve stochastic optimal control problems by sampling. One of the notable achievements of reinforcement learning is this Q-learning algorithm, which is an off-policy method for solving optimal control problems. So here we have a different method. So here's this learning algorithm. You have some approximation to this function z, and you sample and you update in this way. It's very simple. Actually, it's much simpler than Q-learning. And you can see that this is sort of naive Q-learning. This is naive z-learning. Naive meaning sampling from the passive dynamics. You can also sample from some other control policy, which is, say, optimal with respect to your current approximation to z. And when you do that, that z-learning is still faster. And again, there's no mystery here. We've basically done a lot of analytical progress sort of behind the scenes, and now what's left to be solved numerically is a much simpler problem. So of course, we're going to solve it faster. The catch is that we're now restricted to this family of problems, but it turns out it's a rather general family, and a lot of things fall into this. Like, for example, this little car on the hill is one of the standard benchmark problems that people use all the time in optimal control. And the last thing I'll mention in terms of applications is compositionality. So let me go back. So I told you earlier that the solution to this continuous problem satisfies a second-order linear partial differential equation. Linear PDEs have the property that if you take two solutions, you can add them up and you get another solution. Okay? So what that means is that if I formulate several different optimal control problems that have the same dynamics, say my arm, but different final costs, say I want to hit this table, and in one case I want to hit it here, in another case I want to hit it here, in another case I want to hit it here. So I'm going to define some sort of functions over that table that are my final costs, specify where I want to hit it. And suppose for each one of those final costs, I find the optimal way to control my arm. Now, I can take any weighted sum of those final costs, and I'm guaranteed that the optimal solutions are going to add linearly because they're solutions to second-order linear PDE, and the only thing we've changed is the boundary condition. And so this is illustrated here. This is particularly useful in cases where you can solve the individual problems, but the combined problem is something more interesting. So here's an illustration of that. I mentioned earlier that these linear LQG problems can be solved analytically. So here's a very simple one-dimensional point mass. This is position. This is time. It's supposed to go to some position, so there's some quadratic cost-to-go function, and this is what it looks like. This is the optimal control law. We can now compose two of those and get some final cost that sort of looks like that. So there are two good places to go to, and you can pick which one to go to. And then we can compose these surfaces in closed form. So this is an example of solving analytically problems that have linear dynamics and Gaussian noise, but non-quadratic final costs. In fact, the final cost has to be of this form. It has to be the log of the weighted sum of a bunch of Gaussians. These H's have to be quadratics to be an LQG. And this is a universal function approximator, so you can actually approximate any final cost that you want, given enough of those Gaussians. Okay, so I took too much time talking about this, but this is the latest thing I'm working on, so I'm somewhat excited about this. Now, what we're doing now is building sort of more powerful algorithms using these ideas and scaling them to harder problems. If you're going to solve harder problems, you need to be able to simulate interesting dynamics. So a couple of months ago, I just took a month off and wrote a really good simulator for arbitrary dynamical systems. It's based on the Open Dynamics engine, and you basically write XML files to specify out the model. Let me show you. So right now, this is not being controlled. It just has some passive dynamics. Really interesting feature of the simulator is that I can plug in the 6-degree freedom mouse, and then I can apply forces into the simulator. So I can select objects, and I can make them do things. And right now, this is not very useful. Well, I mean, actually, it may be a very good way to do keyframe animation, because this is a very intuitive sort of interface. I can drop the whole thing. Just false. Nice thing about this is that it's actually interfaced to Matlab. So from Matlab, you can tell the simulator to load an XML script with whatever model you want, and it simulates it, and it gives you the state, and then you send it control signals. So we're going to be using that to simulate various interesting things. Another thing we're doing to define hard control problems is actually getting into robotics. So my students are building this modular thing that basically has 3 degrees of freedom, like 2 here and 1 here. And then once you have that, you can hook up 2 of them and you can have a biped. Or you can hook up 4 of them and have a quadruped. Or you can hook up 5 of them and turn it upside down and you have a hand. So we're trying to use this module to do both locomotion and hand manipulation. And the key to it is using some very small but very powerful motors so that we can get away with cable drives with very small torque amplification, so the thing is fully compliant. And the thing is indeed really compliant. It's quite amazing. We're also collaborating with Yoki too and hoping to use her really complicated hand. I hope we manage to control this thing someday, but I'm sort of more optimistic about controlling this thing in the short run. Okay, so we have tools to solve optimal control problems, and now we want to use them to understand behavioral data and build good models of it. And I should say there's a long history of that. I mean, there are models of this sort go back at least to 1970 and perhaps earlier. What I have specifically contributed is move away from sort of open loop optimization, which people have tended to do, and look at closed loop optimization and figure out how to control stochastic sort of redundant system optimally. And so when you do that, turns out something very interesting happens. So let me just illustrate that with a simple example. So this is the simplest possible redundant system. It has 2 state variables, and we want to keep their sum equal to a target. A real-world example of a redundant system is, I want to press this button. I can do it like that. I can do it like that. I can do it like that. I can do lots of different things. So in general, your body has a lot more degrees of freedom than what you need to accomplish any one task. And the reason is because you want to be able to accomplish lots of tasks. Okay? But the flip side is that now in the context of a given task, you have to figure out what to do with all these degrees of freedom. Right? So it gives you flexibility and sort of power, but at the same time, it presents a challenging control problem. When people design machines, they tend to stay away from that. You design a machine for one specific task and it has the minimum number of moving parts that you can get away with, and that simplifies control. But then if you want to do something else, you have to build another machine, and biology doesn't work that way. So simplest redundant task, 2 state variables. We want to keep their sum equal to a target. This is the state space, x1 versus x2. Now, if the state varies in this direction, the sum of x1 plus x2 is going to change. So you don't want to allow sort of noise in that direction. But if the state were to vary in this direction, that's actually OK, because the sum of x1 plus x2 stays constant. Okay, so this is characteristic of any redundant task. There are sort of submanifolds in the state space where the system can move around freely, and that's not going to affect the task performance. Okay? So if you analyze the optimal controllers for such tasks, they sort of have this property that if you depict them as little force fields that are pushing the state somewhere, they're pushing it towards that redundant manifold, and they don't really care where it is. As a result of that, if the system has noise in it and the control law is pushing that way, you're going to end up with sort of variability that's sort of elongated this way. So you have a lot of variability in aspects of the movement that are not relevant and you don't need to care about. And you have less variability in dimensions that you care about. Why is that a good thing? For 2 reasons. One is that obviously this arrow is shorter than an arrow from here to here. So in other words, if I were to try to get rid of the redundancy and say that I'm just going to aim for this point no matter what, I could have a control law that pushes towards the center, but then it's going to take more energy, obviously. The other reason this is optimal is because the noise in the motor system scales with the magnitude of the control signal. So the more you activate your muscles, the more the force output fluctuates. And there's some physiological explanations of why that is, although I don't think they're complete. But whatever the explanation is, just an empirical fact. Okay, so what that means is that when you activate your muscles too much, you're not only going to fatigue yourself, but you're also going to make your movements less accurate because you are injecting, whenever you act, you inject noise, basically. So action is bad for 2 reasons. Okay, so what that means is that we should expect more variability in dimensions that are irrelevant. And indeed, there's a very rich experimental literature showing that, and I'm going to illustrate with some experiments from my own work. The other thing this gives rise to is, like if you notice these 2 command signals, U1 and U2 are basically the command signals that change these 2 variables. They're coupled. Like whenever you have some force field that's parallel, that means that things are somehow correlated. And both of them are functions of this x1 plus x2. In other words, the controller is not looking at the individual state variables, but it's only looking at some sort of high-level feature, which is what matters to the task, right? So in this case, it's the sum of these two things that matters, and that's what the optimal controller looks like. And that function has some form which I'm not showing. Okay? That leads to another important concept in biology that has been around for probably a century now, and that's called the motor synergy. Okay? What that means is you have lots of degrees of freedom, lots of muscles, but the idea is that you don't control them independently. Instead, you couple them, and you create some sort of high-level control knobs. And then as you turn those high-level knobs, there's some distributed action that goes to all your actuators. And that hopefully simplifies your control problem. And if you couple them the right way, you're still accomplishing the task, but now you're working in a reduced space. Okay? And so in this simple cartoon, at least, that falls out of sort of optimality without sort of any coupling on purpose. That's just the optimal thing to do. Now here are a couple of experimental examples. So here this person is asked to point to targets on his body with this pointer. There's a 6-degree of freedom sensor here, so we can compute the positions of the two tips. Several subjects repeat this thing many times. We normalize trajectories in sort of a sensible way, and we compute the positional variance of these tips of the pointer over the path length, averaged over the movements in subjects, etc. So you see two things. One is that tip 1 is controlled more accurately than tip 2. Okay? And that's the working tip. The other thing that you see is that the variability is reduced at the beginning and end of the movement where you have to be at the target, but somewhere in the middle, the brain allows the hand to do whatever it wants. And so you get substantially larger variability. Here's another example. This person has to reach around this obstacle and hit this target. This is the positional variability is plotted with a sort of M&M ellipsoid that captures 2 standard deviations of the noise. And like I said, there are tons of examples like that in the literature. I'm just showing you some from my own work. Here's another example of that, which is in the time domain. So this is an experiment we did. So you put people on a table and you ask them to move their finger through targets. And there are 2 conditions. In one condition, there are only the black targets shown. And in the other condition, all these gray targets are shown. The gray targets are chosen such that they lie on the average trajectory in the black condition. Okay. So if all you care about is tracing some sort of pre-specified trajectory, then there shouldn't be a difference between those conditions. But if what you care about is hitting the targets and not what happens in between, then these 2 conditions are indeed different. And so what we find is that the average trajectories in the 2 conditions are the same, but the positional variance is different. So this is human data. This is how the variance goes up and down just when you're hitting the targets. When you switch to the 21 targets, this plot sort of becomes more uniform. And an optimal control using LQG techniques sort of does the same thing. I already hinted at that, but let me just be more clear. So the way we build these optimal control models is that there is an energy cost, which is quadratic in the control signals, integrated over time. And then there's state costs. And the state costs penalize the positional difference between the fingertip and the targets at specified points in time. So the cost functions that we use are very obvious and sort of directly taken from the task, while the details fall out of the optimal control framework. Now, if it's okay to allow variability in redundant dimensions, and that's variability due to sort of unpredictable noise, then you would also think that if something pushes you systematically in a redundant direction, you don't need to adapt to that. Now, adaptation is generally a process where the world somehow changes in a systematic way, and you figure out what the change is, and you change your behavior so that you cancel it. Classical example is prism adaptation. If I put prisms on your eyes, you see things displaced, you make errors, and after a few movements, you point at the right place. So you recalibrate your visual system and your motor apparatus. So here's an experiment showing that if the systematic change perturbs you in irrelevant directions, you don't actually adapt, which is sort of quite surprising given the literature on motor adaptation, which just says that you adapt to anything. So here's the experiment. So people are making movements using this phantom robot, and it can create forces. This is a virtual reality setup, so the targets here, if you look here, they appear to be down here. So we set up the experiment so that we can impose either spatial or temporal constraints on the movement. So in the spatial condition, we're going to tell you where the movement should end. So there's a target that's small and you have to hit it. But when the movement ends, it's up to you. You can make a fast or a slow movement, that's fine. In the temporal constraint, the target is actually very large spatially, so you can stop the movement at many different places, but the time when you stop the movement is very tightly controlled. And if you get it wrong, the computer beeps and is unhappy. Okay, so this is a space-time plot. This is where the movement ends, so you can think of these as constraints. You have to fall inside that to satisfy the task. So initially, in a baseline block when there's no forces, the movements end here. Now, on the first few trials where we apply forces, depending on what force field we apply, there's some disturbance. So in this case, subjects end up here. In this case, subjects end up here. There's two different force fields. And now in each force field, we test it in each of those different task constraints. And it turns out that the adaptation really depends on the task. So if you're perturbed over here, and you're in this task, in the spatial constraint, then you sort of go here. But if you're in the temporal constraint, you don't go back to where you started, you go somewhere here. And vice versa for the temporal constraint. So that's one of the first sort of pieces of evidence that adaptation is really task-specific. And even though people could have adapted to that, they chose not to because they didn't have to. We're so behind. I have no idea. Okay. I mentioned earlier that optimal control signals end up being coupled, and that leads to the notion of hierarchical control. Hierarchical control meaning, like, don't try to control the individual state variables, but some sort of higher level feature of the state. Well, if we know that, in other words, if we know that for a redundant task, the optimal solution will have that property, then we might as well build that property in advance before we go through some long and painful optimization only to find out the properties there. Okay, so that's the rationale behind scheme for hierarchical control that we have developed, and there are lots of details to it that you can read about. But the general idea is the following. You have a plant or a dynamical system you want to control, and you're going to break the control on two levels. So the state goes into some low-level controller, and then that sends some sort of abstract state representation, some like reduced task-dependent thing called Y to a high-level controller. High-level controller is going to do optimal feedback control and send some high-level command signal V. And then this low-level controller is going to take that and translate it into a signal that's suitable for the plant. Okay? So the key is that the low-level controller is not trying to accomplish any specific task. All it's trying to do is augment the plant and turn it into a different plant which is easier to control and somehow operates on the task level. So just to give you an example, suppose I want to control my fingertip position in space. Now, this high-level thing Y could be just my XYZ coordinates of the fingertip. Okay? And then the high level is presented with an augmented plant here, which basically has the dynamics of a point mass floating in space. And then the low-level controller takes care of the translation between muscles and joint angles and endpoint coordinates. Okay? So both of these guys are still running in real time in closed loop. And this guy is looking at fingertip errors and correcting them in real time, but he doesn't have to worry about all the joints and muscles and such. So the high level knows what the goal is and keeps track of the task-relevant variables, but doesn't know about all the details. The low level knows about the details of the biomechanics, but has no idea what the task is. All it's doing is an instantaneous translation from high level to low level signal. So in the example I gave you, the high level might specify a desired acceleration of the fingertip, and then the low level will figure out muscle activations that will accomplish that desired acceleration right now. And well, there's some math of how we do that, and I'm afraid I'll have to skip that. I should mention that this is related to some really important things, like feedback linearization is closely related to this. There's something called operational space control in robotics that is also related. But what we're doing has interesting differences, and you can read all about them here if you want. So let me just give you an example of using this. So this is a pretty elaborate biomechanical arm model. So we wrote this toolbox that allows you to create these virtual obstacles, and then the muscles are forced to wrap around those, and that allows us to model how 3D muscles change their pulling directions as the arm moves around. And then the muscles are modeled quite realistically. They have this, their force depends on the length and the velocity of the muscle in addition to the control signal. So we put all of that in. We use this hierarchical control scheme. We ask the hand to go from here to some target up and then go down, and then it finds a plausible trajectory, and it finds some muscle activations. We don't know how close to optimal these are, simply because we have no other way to solve this problem. So there's no way to know what's optimal here. But it's plausible and it may be good enough. And so this is exciting for two reasons. One is that we can actually use it as a model of sort of unconstrained 3D human movement. The other one is this. So you probably heard about brain-machine interfaces, people like sticking electrodes in various parts of cortex and trying to decode motor intentions in real time. Suppose you had the technology to do that. And suppose you have a paralyzed patient whose muscles are intact and whose brain is largely intact, but the two are disconnected. Now, you could implant muscle stimulators, and technology is getting better and better. These are the biomes developed by Jerry Loeb at USC that seem to be working really well. So with this technology, you can basically take over somebody's limb. But the question is, what control signals are you going to send if you take over? Right? We don't really have methodologies to do that right now. This is a particularly appealing setting because here we have an intact brain, which is generating basically these high-level commands that tell you where the hand should be going, or at least that's what we are able to decode from it. And then this hierarchical control scheme is ideal for this application. So here the high-level control is actually the brain. This thing is decoded by some brain-machine interface, and this is a formula that takes some microseconds to compute. And so the only challenge here is actually to build a good biomechanical model of the patient's arm, but we can do that through system identification once these things are implanted. So I think this is very promising. In fact, we recently got an NIH grant to pursue this further in simulations, and hopefully we'll, if that works, I'll talk to Jerry Loeb and company about testing it for real. They have patients implanted with these things, but right now they're just used for tonic excitation, like preventing the shoulder from falling from the socket, for example. They're not really used for functional tasks yet. I'll have to, this is a really cool psychophysical experiment illustrating yet another aspect of optimal feedback control and how it applies to data, but I will have to skip it. It was published in Journal of Neuroscience last year if you want. Actually, here we build a pretty big optimal control model and use one of those NVIDIA video cards with 128 processors to build it, and it's 30 times faster than a fast Intel CPU, so that was a good thing. They just released a new version called GX2 that has 256 processors, and I just bought one. It's really exciting. And you can also play video games. Now, the last thing I'll talk about is using these ideas to model what neurons do. Now, whenever somebody shows you models of neurons, you should be very skeptical because we don't really know what neurons do. And you should be equally skeptical of this. The reason I like this is because we have a framework which works well on the behavioral and on the system level. You know, it makes sense sort of philosophically to be optimal. It gives rise to parsimonious models. They agree with behavioral data better than any other class of models we have. And so then the question is, if you were to implement one of these optimal controllers with a neural network, what would that neural network look like? Okay? And if you do that, you're really getting predictions from first principles about how neurons should behave. So that's what we've been doing. And I'll briefly illustrate two studies. The first one is sort of more modest but complete, and the other one is very ambitious but still open. So the first one is a specific model of this data set. So this is some data collected by Peter Strick and colleagues. Let me first tell you a little bit about motor cortex and what people have been arguing about to understand why this is important. So one of the big debates has been, does motor cortex encode abstract things like directions of movement in Cartesian space, or does it encode low-level things like muscle activations or something closely related to those? And there's data to support both, and it's a mess. This study was designed to answer the question once and for all, and it didn't, but it didn't in a very interesting way. So here's the study. So monkeys are asked to make reaching movements with the wrist. So the wrist is here, and targets are presented around the wrist, and it has to reach up, down, left, and right. And they do that in different postures. So suppose I show you a target here, and you move up. And now suppose I show you, you turn your hand, and I show you the same target, and you move up. Okay? And suppose now you record from a neuron in monkey's motor cortex. Okay? If that neuron cares about movement up in Cartesian space, independent of any muscles or joints or such details, then the firing of that neuron should be the same whenever you're moving up, regardless of whether you're in this posture or this posture. Okay? On the other hand, if the neuron cares about muscles, then you need a different muscle activation pattern to do this versus this. Okay? Now, a way to quantify it is to compute something called a preferred direction. So the way you do it is you ask the monkey to move in every possible direction. You record from the neuron, and you find the direction of movement for which the neuron is most active, or you take the circular center of mass. Okay, so you compute the preferred direction for every neuron. You do that in these two extreme conditions, and you see how that preferred direction changed. Okay? If the neurons were encoding things in Cartesian sort of world coordinates, then there should be no change. So this shift of preferred direction should be centered at 0. It's called extrinsic. If the neurons were doing something like muscles, then they should be, in this case, about 70 degrees. How we know that? Well, you can actually record from muscles, and you can see what they do. So that's what they do. Okay, what happens in M1 is something right in the middle. Okay, so it's neither this nor this. It's a big mess in between. So why should that be? So here's the optimal control model that sort of reproduces that somewhat surprisingly. So here's the really simple model of that. So we're going to have an array of neurons that are recurrently connected. We're going to call that M1. And they're going to project linearly to two motor units, say two muscles that pull along the x and y directions of this space. And the trick is that when the posture changes, then your muscle pulling directions are going to wrap around. And so if you think of these two numbers as being the components of some vector shown here, when the posture changes, that vector has to rotate to compensate for the postural change. Okay, the inputs are going to be some sort of cosine hill of activity that's mapped onto this array. And that's going to encode the target input. There's good evidence that such signals come from premotor cortex. And then if the target direction changes somewhere, then this thing is going to shift and also can scale. And the postural input is going to be this sort of irregular thing. So half of the neurons are going to like that posture, and they're going to receive a lot of activation when monkey's in that posture. The other half neurons are going to like the opposite posture, and they're interlinked. In other words, there's no correlation between the postural preference and the directional preference, and that's true in the data. Okay, so we give it those two signals. We ask it to control the output here. So the key is to notice that there are a lot more neurons here than here. We only specify desired output here. So we're effectively letting the network to do whatever it wants. Like it can choose whatever neural representation it wants as long as it accomplishes this task. Okay, and after you train it, you get a histogram of the shift of preferred direction, which is right in the middle, and the mean matches very well. Now you might think that this is a neural network and it can be getting stuck in local minima, and so it learned a mess because it couldn't learn a clean representation. That's not the case. And so in fact, we've run literally thousands of simulations to show that this is the global minimum. Here's one of them. So this is iterations of learning or gradient descent. And this is how much shift there is on the population level. And in the freeze, the sort of the baseline condition, this is what it does, devolves, stops somewhere here. Now we can train other networks which are told what to do. So one class of networks are forced to put this thing at 0. So there are special cost terms that we can put in that require that. So we train them for a while, and then we release them, and then actually they go here. Alternatively, we can ask it to act like muscles, so go all the way to 70, and then we release them and go back. So even if you put a network in a condition where it's using a clean representation, it doesn't actually want to do that. It wants to use this mixed thing. So we spent a lot of time figuring out what are the factors that determine why this is optimal. And it turns out that's noise. It's actually very interesting. So if there is enough noise in this system, and you have diverse forms of noise, and I apologize, but I won't have time to tell you what diverse means. Anyway, if you have enough noise, then the optimal thing to do is use some sort of intermediate strategy, which seems to be robust to noise. If you don't have enough noise in the system, and you basically train a deterministic network, then there are local minima everywhere, and there's no reason why this solution will be better than any other solution. So that was the sort of surprising finding, that it's really the noise that determines what is optimal. And in retrospect, that's not so surprising, because controlling a stochastic system is just a completely different game from controlling a deterministic system. And noise really puts very strong constraints on what solutions are plausible. And lots of things that make sense deterministically, once you inject noise into a system, the vast majority of them break down, and very few survive. We can analyze the mechanisms that do that, and we can find some interesting things that the algorithm discovers. And I won't have time to show you this beautiful math. I have to end in like 2 minutes, right? Yeah. So let me just flash one more thing. So what I just showed was motivated by a specific experiment, but it was a relatively simple thing. Now, the more complicated thing we're doing now is this. So we start with this picture where we have a biomechanical simulation, then some optimal estimator, optimal controller, and this is the algorithms we've been developing all along. But instead of doing that, we can replace this with a neural network. It's going to have the same inputs and outputs as our optimal control machinery, but it's just a bunch of neurons creating some nonlinear dynamical system. So now this is running in loop with that arm. We can optimize that. And it gives rise to some, so this is a reaching task, this is speed profiles, this is what the sensor inputs are, neurons. We can visualize the activity of the neurons for movements in different directions and over time, and we'll get various interesting things. And then we haven't really analyzed the circuits that emerge yet, but we have done some population sort of measurements to convince ourselves that this is a sensible model. And it agrees on the population level with a number of measurements. So this is, what this shows is that if you get a monkey to make reaching movements to various targets, and then record the activity of the neuron while it's at the final target, and you plot the activity on the vertical axis over the plane, then you get basically a sort of a linear plot, and you get sort of similar things in the network. This shows that if you record from a neuron over time as the monkey moves in the direction that the neuron likes, what you get is something that sort of goes up and down, and it looks like a speed profile. That's important because if you believe that neurons are controlling muscles, and if you think that muscles are acting like motors, then you might think that this would look like an acceleration profile, right? Because the motors have to accelerate the arm, but then to make it stop, they have to decelerate, and the negative acceleration should be equal to a positive acceleration, right? So, in fact, these kind of findings were one of the reasons why people started believing in these abstract Cartesian encodings of targets rather than more low-level muscle things. Now, in retrospect, it turns out that was a mistake because muscles are not actually electric motors. Indeed, they have a lot of damping in them, and anything controlling muscles has to compensate for that damping. And the compensation signal for muscle damping basically looks like a speed encoding, and that the damping is so much that it actually dominates the acceleration signal, it turns out. So I explained that in an earlier paper, which didn't have a neural network in it, just reasoned about biomechanics, and now this network is sort of doing this thing. This is another cool thing, which I'm just, well, this is the last slide, so I might as well explain it. This is an old experiment that was also attracted a lot of attention at the time. So that was done by Emilio Bizzi and colleagues at MIT. So here's the experiment. You put a monkey in a setup, and the monkey is instructed to reach for some target. You couple it to a really strong robot, and then just before the monkey reaches, the robot pulls the monkey's arm to the target. Okay? So now the robot does the job of the monkey before the monkey can begin to do it. Okay? Now what happens is that you think that the optimal thing to do is just take advantage of the robot, and once it takes you to the target, stay there. Don't move. That's not what happens. So this is time here. This is the force that the robot applies. Arm is drawn to the target, and then once it's released, it actually goes back and then goes forward to the target. Okay, so this was one of the most convincing pieces of evidence to suggest that there's some sort of reference trajectory that the brain wants to follow. And if you're displaced from that, then the brain fights to return back to it, even if the displacement was actually convenient. So surprisingly, this network ends up doing just that. So here we're perturbing it, we're taking it all the way to the target, it fights back and goes away. If we don't perturb it, it does that. Now that's bizarre because this network is trained to be an optimal controller, and an optimal controller would never do such a silly thing. So why is the network doing it? Well, the network is doing it because the network is trained with a small amount of noise. It's never trained with these very large perturbations. So in the regime where you train the network, it approximates an optimal controller reasonably well. But if you put it outside that regime, it switches back to some more primitive strategy, which is basically a servo controller that's fighting anything and to save its life. And so it ends up doing that kind of thing. Okay, so it's time to end here and just close with some future direction. So in terms of the neural data, we need to do more work to analyze the mechanisms that emerge through learning. And we've already done some of that. I just didn't have time to talk about it. Another important thing is to introduce neuroanatomical constraints in those networks. So for example, the thing we're doing now is putting the neurons on a two-dimensional grid and allowing only local connectivity. And we're still training the connections, but now the network is forced to do some sort of local computation. And the idea is to see if anything gets mapped onto that two-dimensional surface. Because you probably know that in visual cortex, for example, there's a map of the visual world. Right? So if you record neurons in view 1, the receptive fields of the nearby neurons are nearby in space. And there are maps in auditory cortex of frequency, and there are maps in the somatosensory system of position on the skin. In the motor system, people have been surprisingly unable to find maps of anything. And it's not clear it's because they don't exist or the quantities being mapped are so complicated and counterintuitive that we don't know what to look for. So these models will tell us, does it make sense to map anything? And that's exciting. On the behavioral level, we are looking forward to develop those hierarchical feedback controllers. We're also moving towards looking at motor adaptation as a form of re-optimization. I just showed you one example. On the algorithmic level, we're going to push these new methods based on this duality and linearity of the underlying equations, and we'll hope to scale them to more complex problems, especially those involving contact, like manipulation and locomotion. Contact is critical because, well, the way you interact with the world is through contact. Contact causes sort of discontinuities in the dynamics, and most of the efficient algorithms we have are going to fail because they rely on derivatives, basically, and you don't want to be taking derivatives when you have contact. The beauty of these new algorithms is that they're sampling algorithms. There's no derivative anywhere in them. So that, I hope that would really allow us to go around the issue of contact. Right. Thank you.